So what is precalculus about? Here's an overview of all 24 of our topics in 24 minutes. In our first topic area, we reviewed key techniques of algebra, and we were introduced to our object of study throughout all of the course, functions and their graphs. First, we looked at strategies for simplifying expressions that involve exponents. This included converting radicals into fractional exponents, such as this square root into an exponent of 1/2. It included distributing powers over multiplication and division. Don't forget that this applies to the numerical coefficients also. Converting division of powers into subtraction of exponents, and turning negative exponents into positive by trading multiplication for division to completely simplify an expression involving exponents. Because polynomial and rational expressions play a key role in defining the functions we care about later, we reviewed strategies for factoring and simplifying them. It's usually a good idea to factor rational expressions before doing any arithmetic with them, because here, for example, it helps us to find a common denominator that we need in order to add or subtract our rational expressions. Once that addition or subtraction is all done, the step that you're most likely to screw up in this process is probably the simplification that comes at the very end. Remember, terms that are added or subtracted in the numerator and denominator cannot be reduced or canceled. Only entire factors of the numerator and denominator, such as this x plus 4 up here, can be reduced or canceled. Finding and using formulas for linear relationships is a vital skill for both precalculus and for calculus. If I want to discover, for example, when this green line falls beneath this purple line, we first are going to need to find an equation for the former, and it suffices to find and use its slope along with a single one of its points. The slope of a line is the ratio between differences in y values and corresponding differences in x values. The point slope template then helps us to use that slope along with any known point on the line to determine an equation for that line. If we solve that equation for y, we can then ask when are the green y values beneath, less than or equal to, the purple y values. This sets up an inequality which we can solve, remembering to reverse the inequality when we multiply or divide both sides by a negative quantity. We obtain that x is greater than or equal to 8/3, which is visible on my x-axis on the graph, and I can express that answer in interval notation that includes a square bracket which includes 8/3 in our answer but does not include infinity because it's not a number. Functions and the ways in which they model relationships among changing quantities are what precalculus and calculus are actually all about. They're useful because they're deterministic. They relate each one of the inputs in the domain to only one output in their range. For example, because each person in the US has one and only one biological father, the assignment of person to dad is a function, and the domain of that function is the set of all US persons. On this graph, by contrast, there's a single x value that corresponds to more than one y value. This vertical line meets the graph in more than one location. And therefore, this graph fails what we call the vertical line test, and therefore does not depict y as a function of x. The data table in the upper right here has a repeated x value, but since its corresponding y value is the same both times, we can still say that y is a function of x here, and the domain is going to consist of the set of all x values that we can see. Finally, an equation that relates x and y together can be solved for y to determine whether it depicts y as a function of x. In this example it does because the expression that we obtain is single valued. The domain of that function, on the other hand, has to exclude the value x equals 0 because that value makes the denominator of this expression 0 and therefore the expression that defines y undefined. So the domain is all real numbers except for x equals 0. The graph of a function depicts all the points in the Cartesian coordinate plane whose y-coordinate is equal to f of its x-coordinate. While pictures can speak 1,000 words, they don't always do so with precision. But we can read the domain of a function off of its graph by squishing the graph onto the x-axis. And we can read the range of a graph by squishing that graph onto the y-axis. We can read the x-intercepts of a graph as the places where that graph crosses the x-axis. In other words, the points at which the y-coordinate is equal to 0. Conversely, the y-intercept of a graph is the point on the graph where the value of x is equal to 0. Given any x value, We can find the value of f of x by reading off the y-coordinate of that graph's corresponding point. And going the other direction, given a value of f of x, in other words, a y value, we can solve for x by reading off the x-coordinate of the graph's corresponding points. And in these cases, there can in fact be more than one. Graph transformations help us to graph complicated functions by beginning from a simpler basic shape. Transformations come in two basic flavors: multiplications, which we want to do first, that can reflect, stretch, or shrink the shape of a graph, and additions and subtractions, which we want to do last, that can shift the graph's location in the coordinate plane. Applying these operations to the y variable outside of the expression that defines the function has a vertical effect on the graph, while applying them directly to the x variable has a horizontal effect. But remember that the x effects can be counterintuitive. For example, replacing x with x plus 5 has the effect of shifting the graph to the left by 5 units, because what we're really doing is shifting the x-axis to the right. The simplest function type that we study models relationships where addition and subtraction in one variable results in addition or subtraction in the other. These are called the linear functions, and the constant ratio between those changes is called their slope. The slope and intercept of a linear model are more than mere numbers. In context, they are meaningful descriptions of a relationship. Given 2 points, there is a unique linear function that includes them both, for which we can find a formula, again by first determining the slope, and then, for example, we can use the slope-intercept template, y equals mx plus b, to determine a formula using a known point to determine the y-intercept. The slope can be interpreted in context by restoring the units of x and y back into the fraction that defines it. In this example, the units are dollars per 1,000 sales. And the slope's meaning says that an increase of 1 in the x variable, here selling 1,000 more pairs of shoes, is going to correspond to a decrease of 0.2 in y, in other words, decreasing the price per pair by 20 cents. As always, the y-intercept of this relationship is the value of y when x is equal to 0, which in context here tells us that 0 pairs of shoes will sell if the price of shoes is set at $120 a piece. Did you know you can have a conversation with a function? If you tell it a value for x, it can tell you a corresponding value for y, and if you're lucky, the reverse is also true. The formula for this linear model from the previous example permits us both to specify an x value, 200,000 pairs of shoes sold, and ask for its y value, the price. And we can also specify a y value, in this example a price of 0, and ask for its x value, the number of sales. For the former, we need only to evaluate f of 200, which comes out using our formula to 80. For the latter, we need to solve the equation f of x is equal to 0, which in this example is not so difficult because this is just a linear equation to solve. Notice that since y was equal to 0, what we're really talking about here is the x-intercept of this graph. When we place this back into context, never forget to re-include your units when placing your answers into a real-world situation. In this example, $80 per pair was this price, and 600,000 pairs was this quantity. Now, the real world is rarely as simple as a linear function, but often it gets close. A linear regression is a way to discover which linear equation matches a set of data points better than any other linear equation does. We can use technology to find a slope-intercept equation for this line of best fit, as well as its correlation coefficient r, whose sign tells you the direction of the correlation. Here, fairway accuracy for golfers decreases as their average drive distance increases. And the magnitude of that correlation coefficient tells us the strength of the correlation. Here, this number is pretty far away from 1, and so this is not a terrific linear model for this data. Because this equation captures an overall trend, we can also use it to make general statements about the data by, for example, interpreting its slope, or making specific predictions about new data points by evaluating or solving this equation for a given x value or for a given y value. The next level after linear functions are quadratic functions, which can model behavior that has a maximum or a minimum point. Quadratic functions can have as many as 2 x-intercepts, and how many they have is determined by the sign of the discriminant b squared minus 4ac. Finding the x-intercepts themselves, on the other hand, is a matter of solving a quadratic equation. which in the best of times is a factoring problem, each of those factors matching one of our x-intercepts. That's going to become a recurring theme for us. As always, the y-intercept is the value f of 0. Graphs of quadratic functions, called parabolas, are symmetric across a vertical axis whose x-coordinate can be found by dividing minus b by 2a. The vertex, the maximum or minimum point of the parabola, can be found at this x value, and we can find the y value of that point by evaluating our function at that x value. Since every parabola is a graph transformation of the basic shape y equals x squared, that means that this vertex also tells us the horizontal and vertical shifts that are necessary to create this parabola from graph transformations, and the leading coefficient a tells us the vertical stretch. To optimize a quantity is to determine where it reaches its maximum or its minimum value. In general, we need calculus to carry this out, but for quadratic functions, we only need to find its vertex. Respectively, a parabola that has a negative leading coefficient is going to reach its maximum value at its vertex, and a parabola with a positive leading coefficient attains a minimum value at its vertex. In this example, we can find how to maximize sales revenue simply by finding the x-coordinate of the vertex in the usual way, minus b over 2a. This gives the number of pairs of sneakers in thousands that we have to sell in order to achieve that maximum. And the y-coordinate of that vertex gives us the amount of sales revenue that's attained at that maximum. As always, when we place this information back into a context, don't forget to include the units. When 300,000 pairs are sold, $33,300,000 of revenue is generated. To solve a quadratic equation is a well-worn algebra skill. But what about an inequality? By rearranging a quadratic inequality so that it has a 0 on one side, we can reduce it to the question, how does the sign of this quadratic expression depend on the value of x? And the best way to understand the answer to that question is to find the factors of that expression. Because after all, if we know whether each of these factors is negative or positive, we will know how they multiply together to determine whether the whole expression is negative or positive. We can use a sign chart to keep track of this information by first finding where each of my factors becomes 0, and then listing the sign of each one of those factors on either side of the x value at which it becomes 0. Multiplying those signs together is going to give me the sign of the whole quadratic expression. And since in this example our inequality is satisfied when that expression is positive or 0, we keep only those pieces of the number line at which this expression is positive or 0. We then can express our answer in interval notation as the union of those two corresponding closed intervals. Quadratic functions introduced us to the role that leading coefficients play in governing which direction the graph points, opening upward or downward. That's called end behavior. They also showed the role of factors in determining the nature of the zeros of polynomial functions, called local behavior. So what if we have more than just two factors? And what if we can not only multiply by those factors, but divide by them as well? The higher degree polynomials and the rational functions that we can study are going to look more complicated, but much of the story remains the same as it did for quadratics. A polynomial function is defined to be a sum of multiples of whole powers of x, the highest power of which is called the degree of that polynomial. That degree is found in the leading term, and that leading term governs the polynomial's end behavior. Even degree polynomials originate and terminate in the same infinite direction, whether positive or negative, while odd degrees originate in one and terminate in the other. The sign of the leading coefficient then tells us which end is up on the right side of the graph, as x tends to positive infinity. While the y-intercept, as always, is a simple matter of evaluating f of 0, finding the x-intercepts, or the zeros, of a polynomial is much more challenging, and it's best done by placing the polynomial into its factored form. Just as with quadratics, each one of those factors gives rise to a 0 of our function. When those factors are repeated more than once, we say that their exponent is the multiplicity of that 0. Those multiplicities tell us the function's local behavior, the shape of its graph, near each of those zeros. Taken together with the end behavior, this helps us to sketch the entire graph of the polynomial function. In addition to end behavior and local behavior near zeros, the number of turning points, the local maximum and minimum values analogous to the vertex of a parabola, can also give us important information about a polynomial function. The fundamental theorem of algebra guarantees that a polynomial cannot have any more real zeros than its degree, and also that it cannot have any more turning points than one less than its degree. When I combine those two pieces of information with the end behavior that gives you the sign and the degree, and the zeros that give me which factors that we want, we're going to have enough information to be able to predict a formula for a custom polynomial that has all of the features on its graph that we're looking for, made to measure. The only thing we need to do at the end of this process is adjust our leading coefficient so that we get exactly the y-intercept that we desire. When it comes to polynomials, where there are zeros, there are factors, and this relationship is so tight that we can use any known zero of a polynomial function to predict one of its factors. And from there, polynomial division is a strategy that can help us to determine the quotient and continue to factor. This process of dividing to find the cofactor can in principle continually be repeated until my polynomial is completely factored. And once it's completely factored, we have therefore found all of its zeros. What's more, polynomial division also has the ability to evaluate a polynomial function. To evaluate f at a given value, x equals a, just divide f by x minus a and take the remainder. When we find that remainder is exactly the value of f at a. And in some cases, this can be faster than just plugging in that x value in the first place. A rational function is nothing more than the result of dividing two polynomials. The zeros of the polynomial in the numerator predict the possible x-intercepts that function can have. But the real action happens in the denominator, whose zeros are going to make the function's value undefined. The zeros of the denominator are therefore the excluded values of the domain of the function. And notice that this remains true even when one of the factors in the denominator might happen to reduce completely with a factor in the numerator, such as these x minus 2's canceling out. Even after simplifying, that value still needs to be excluded from the domain. Just as with polynomial functions, the end behavior of rational functions is governed by leading terms, only now it's the combination of the leading terms of the numerator and the denominator. When their quotient is a non-zero constant, as it is here, that constant gives us the function's horizontal asymptote. If the degree of the denominator happens to exceed the degree of the numerator, then that horizontal asymptote is always y equals 0, in other words, the x-axis. When the degree in the numerator is higher than the denominator, there is no horizontal asymptote at all. But when that degree is exactly 1 higher than the degree of the denominator, we get a slant asymptote whose equation can be found through polynomial division. Meanwhile, by factoring my rational function completely, we'll be able to determine the local behavior of the function near the excluded values in its domain. A denominator factor that reduces completely corresponds to a removable discontinuity, or a hole in the graph where that factor becomes 0. A denominator factor that does not reduce completely corresponds to a vertical asymptote where that factor becomes 0. And a numerator factor that does not reduce gives us an x-intercept. Now, near any vertical asymptote, we can make a sign chart of all the expression's factors, and then use that sign chart to classify the function's local behavior near that asymptote. Whether it goes to positive infinity or negative infinity on each of the left side and the right side of that vertical asymptotes can be determined by a sign chart. Putting it all together, we have a strategy for customizing a rational function whose graph has whatever properties that we desire. To create an x-intercept, for example, we'll place a factor in the numerator that vanishes at the desired value of x. If we do the same in the denominator, we can create vertical asymptotes. By repeating those factors, we can change the local behavior, repeating an even number of times to make the local behavior match on either side of the asymptote, and an odd number of times to make the local behaviors opposite on either side of the asymptote. We can create a removable discontinuity, or a hole, by placing that factor in both the numerator and the denominator. And finally, as with our polynomial example, we can adjust the leading coefficient as well as the degree of the numerator and the denominator until the end behavior and or the y-intercept that we want are exactly right. In this example, all we need to do is make a leading coefficient negative so that f of -1 can end up being a negative value. The last function models we study are those with the power to correlate addition and subtraction in one variable with multiplication or division in the other. These are the exponential and logarithmic functions, each of which is inverse to the other. By inverse function, we mean a pair of functions each of which exactly undoes what the original function does. That is, each of them represents the very same relation, only the roles of x and y, input and output, have been reversed. Despite the confusing notation, inverse functions are generally not the same thing as reciprocals. Inverses are defined using the notion of a composite function, where the output of one function is fed into the input of another. Composite functions can be evaluated just by following the order of operations. If a function has an inverse, then when it's composed with its inverse, the result is the so-called identity function, whose output is equal to its input, the inverse having undone exactly what the original function did. Finding a formula for an inverse function is simply a matter of reversing the roles of x and y, and then trying to solve the resulting equation. If we can do that, the result is going to give us a formula for the inverse function. Thinking graphically, the inverse of a relation, any relation, reflects the original across the diagonal line y equals x, interchanging vertical with horizontal. But in order for this inverse function to be a function and pass the vertical line test, the original function has to therefore have passed the horizontal line test. A function which does is called invertible or one-to-one. In this example, we're looking at a function that did not pass the horizontal line test, so was not one-to-one, and so its inverse is not a function. An exponential function is one in which addition and subtraction in its input variable is correlated with multiplication or division in its output. When y is an exponential function of x, every increase of 1 in x gives rise to a multiplication in y by a factor of a constant b called the base of the function. This quantity is the exponential function's analog to slope. As with linear equations, there's an equation form for exponential functions that directly uses both the base and the y-intercept. But the base is frequently rewritten as a power of the natural number e, however, and we can find this coefficient r, sometimes called the rate constant, by using a logarithm with a base of e called a natural logarithm. Now, indeed, the very definition of a logarithm is that it is inverse to the exponential function. In other words, the base b log exactly undoes what a base b exponential does, reversing the roles of input and output. That definition permits me to rewrite any exponential expression or equation in a logarithmic form and vice versa. For straightforward examples like these, that rewriting and a little bit of light guessing and checking is enough to evaluate these expressions and solve these equations without the use of a calculator. But when a calculator's logarithm buttons are necessary, the log button gives us a log with a base of 10, and the ln button gives us a log with a base that's equal to the natural number e. Because logs convey the same relationship that exponents do, only in reverse, every power and exponent property in algebra has a corresponding logarithm property. For example, powers inside of a log are multiples on the outside of a log. Division on the inside turns into subtraction on the outside. And a multiplication on the inside of a log turns into addition on the outside. On the other hand, addition or subtraction inside of a log cannot be simplified any further. These properties can be used both to expand a bunch of arithmetic that happens inside of a log, or to collect a bunch of arithmetic that happens on the outside, provided the bases of all of our logs match. Speaking of matching bases, an exponential equation with a common base on both sides can be solved simply by equating the exponents, since all exponential functions are one-to-one. This remains true if we can rewrite one exponential in an obvious way so as to make the bases match. This is the same as taking a logarithm on both sides. But when there's no obvious way to match the bases, any logarithm will do to rescue the variables from out of the exponents, and through the properties of logarithms, make a solution possible. Finally, the change of base formula lets us evaluate a numerical logarithm such as the base 2 log of 3, whose base is unknown to our calculators, by choosing any base that we like and dividing the log of our quantity by the log of our custom base. Again, the properties of logarithms helping us to solve these equations that otherwise would not be possible to gather together. Always check your answers when you solve a logarithmic or exponential equation, because sometimes solutions pop up that are spurious. Finally, we can have conversations with exponential functions by supplying a value for x and asking for y, or vice versa. When I supply a value for x and ask for y, I need only to do some arithmetic following the order of operations to discover that value. But when I supply a y and ask for x, we need to solve for this x in the exponent by first doing all of the algebra necessary to unwrap that power and get the power by itself. Only then can we then take a logarithm with the base that we need in order to rescue the x variable and finish the solution, using the change of base formula or a calculator where necessary. We can also bring back their interpretation of the base of my exponential equation as being the factor by which y is multiplied when x is increased by 1, keeping in mind also that percents are often used as a way of communicating about multiplicative changes rather than multiplicative factors. And that's all there is to our Precalculus course. With this inside and out understanding of these 6 types of function models and how they represent different relationships between changing quantities, you're going to be equipped to tackle calculus next semester, where you're going to study ways of taking any function apart into its infinitesimally small differential rates of change and then integrating those changes back together to recover a function from them. After Precalculus, you'll be all set to go.